Yes, fine, right. So, hello all. I'm Hannes Reinecke. I'm from SUSE, and it's actually my first time I'm here, so thank you for being here and everything, and thank you to Hans for organizing all of this. So, this is a presentation which I was hoping to hold here, and because I found it an interesting topic and also something to, so basically how far you can get with coupling existing things together. So, raising dead sheep. Right, so I am, well, doing NVMe things and trying to develop new features, which is all nice and quite interesting, but as it turns out, most of these features nowadays requires you to have a distributed storage, because only then things get interesting. Then you can do whatever, kill I/O on one side from the other side and trying to fail over things and whatever, and steer I/O to various nodes in the cluster, which is all nice and sounds great and maybe work perfectly if you have a distributed cluster. But if you don't, it's ever so complicated. You can surely fake something, but you know, it's not the real thing. So, what can we do? Or rather, I thought, all right, what can I do? So, once upon a time, there was Sheepdog. Who in this room has heard of Sheepdog? Oh, cool, people do. So it's not quite dead. As I said, not quite dead yet. Oh, that's a cyclic reference. We don't do cyclic references here. Right, so that was a distributed cluster for KVM back in them times, where people started building virtualization clusters based with QEMU and KVM. And if you're building a cluster, well, you will really want to have a distributed cluster storage that you can move things around without having to copy all the time. So that's what is being used for, that's what it had been designed for. And so this is basically just a graph which I actually copied over from the website there. So well, it just shows you distributed storage. So you can remove things, add things, and it will just essentially work. So that was all nice and cool and was actually quite, I wouldn't say heavily used, but was used, most notably by Taobao, if people know who or what Taobao is. So, Taobao is actually the Chinese eBay. So it couldn't be that bad, I thought. Right, so that's a distributed storage. It actually splices data off in 2 gigabit chunks and gigabyte chunks and store these chunks throughout the cluster on any nodes it finds suitable, and have then replication or even erasure coding on the chunks to be more efficient. So all nice and everything, but then, you know, Ceph turned up and everyone said, oh, we have to go to Ceph, and Ceph is superb and everything, and takes over your machine and the other machine, basically all machines which you have, but it's awesome. Oh shit, really, did it?
Yes.
Oh, right.
We were looking at this, but we were looking at Ceph as well.
Oh, okay. Right, okay. Anyway, it doesn't really matter. But then people sort of losing interest into that one, and it got eventually even removed support from QEMU, and that was that. And it looked a bit like, you know, another of the graveyard things to be, destined for obscurity. Okay, but nevertheless, it is still a distributed storage cluster. So, and if people had been using it apparently successfully, it can't be that bad. So what would it take to actually turn that into a storage backend for NVMe? So, first challenge. It is a clustered storage. And as such, you really want to have the nodes talking to each other. For that, they originally put in a cluster interconnect based on the classical things which you do at that point. They actually implemented 2 cluster interconnects on their own until they finally settled over to use CoroSync, which people might know of HA Heartbeat fame, and used CoroSync for that. Okay, but modern things really have gone away from that one and really went to a different model of how cluster communication is done. So they switched over more to a distributed database and ensured that the distributed database is kept in sync, and then everyone could read off that database and you would have the very same thing without having the same thing. So most commonly thing for Kubernetes and stuff is something called etcd, which is precisely that, a distributed clustered storage database, and all nodes can access it. Okay. which means that if I were targeting, say, whatever container deployment, chances are that etcd is already there, or at least the bits and pieces to install etcds are there. So maybe we can use etcd as a cluster interconnect. So there's only one thing. The cluster interconnect typically is actually a message-based interface. So you're sending messages from here to there and broadcasting messages across the interconnect and everything. So, which is nice, but it is a message-based thing. etcd, on the other hand, is more database, which is not quite a message, but rather database. Thankfully, etcd has something called a watch interface, which allows you to, well, put a watch on any value which you are on any key which you care, and etcd helpfully will notify you when someone changes that value, which is quite neat. So you can implement a mailbox thing, where if you want to distribute a message, just write into the mailbox thing, and then every node in the cluster will get notified and sees, oh, someone wrote into that mailbox, which is cool. And you can even roll back, because each message you write there has a sequence number, so you could actually get all the previous messages. So you will not lose messages, irrespective on when you start off. You get the number when you started off, and then once you're ready, you check which numbers are we now, and just get me everything in between. Cool. So, and that works, which means now we have a cluster with 4 nodes here. That's the Sheepdog thing, and everything is connected via etcd. Yeah, nice, cool. So, but then now we have a distributed cluster, which is good, so we can store data. Unfortunately, we don't have any means on how to get the data in or out of the cluster, because, as I said, the KVM frontend has been removed. So, nice to have a storage cluster, but it doesn't actually do storage right now. So, there's an S3 gateway, but then, yeah, it's S3, and come on, really? No, we don't want to. I mean, it should be an NVMe cluster, not an S3 cluster. Right, so, and ideally, we really would want to have something like a block device, or maybe a file, or something which we can use for NVMe. Ming Lai has put in a lot of work to get this uBlock driver to work. Again, question to the audience, who has heard of uBlock? Ooh, okay, nice. uBlock is, block device in user space. So this is basically Fuse, but without the file systems. So you implement a block device in user space, and there's a pass-through thingy layered on top of the IOU ring, which allows the IOs from that emulated block device passed into the kernel, and then the kernel presents that as a block device, which is quite nice because it allows you to basically do everything. Any storage you'd like to design can be presented as a block device. So I said, oh, that's cool. So, and then the users think, how hard could it be to write a uBlock front end for Sheepdog? And as one does nowadays, first thing you do is ask Claude. Hey, or in my case, ask Gemini. Hey, Gemini, wouldn't you mind to do it? Oh, yeah, not a problem. Of course I will be doing that for you. And here's the thing. And you just have to hook it into that function. Nice, thank you. Okay, looks good. Yeah, looks really good. But hang on, the function isn't there. Where did you get that from? Oh, you're right, the function isn't there. Because you have to do that. Right, thank you. So after about 4 iterations, I said, come on. Right. So then back to the old-fashioned way. Okay, so do it myself, because there's still the looked up in the old Git commits from QEMU, so what did you do back in them days when you had it? What do I need to do? And then you coded something and did, and finally it actually worked. And it got merged. Yay, thank you, Ming. So now there is a Sheepdog front end in uBlock. So, which means we can now expose the virtual devices here as uBlock devices to the OS. Right, cool. So now we have block devices there, and then it's, well, quite easy. Yeah, just put an NVMe target on it. So because it's now a block device, we can just create a configuration for the block devices and have a nice NVMe target. Well, actually, we actually have 4 NVMe targets, which is nice, but we want to have a distributed cluster. not 4 of them. So we have now namespaces and everything. Yeah, but we really want to make them appear just like a single subsystem. And so we really have to match them all up. And by the way, these 4 namespaces, they are actually just one. They are actually the same namespace, only, well, not, And of course, there's a configuration, and that all needs to be distributed across the cluster. What to do there? And now I'm afraid we have to delve a bit into the NVMe arcana, things which are not necessarily in the spec. Because it turns out that the subsystem, as defined by NVMe, is actually just a virtual construct. Literally, yeah. Wow. Because it is really just a name. And if that name is present on various devices, the initiator will assume, oh, it's the same thing. So the only task here to do is, well, you have to present the same information to the initiator, irrespective on where it's accessing you. Well, but then again, yeah, you can do this, but then there is some fine print attached to it, because it's not necessarily the same information. Some bits has to be well partitioned that you can get a consistent view of that thing. And so that is then where the real fun begins, because then suddenly you end up with delving really deep into that thing. Because some are actually per controller, so actually per connection. So like the connection ID, which is, well, guess what, per connection. And it needs to be consistent throughout the entire cluster or throughout the entire subsystem. So either you coordinate between nodes, hey, which number do you have? Can I use that number? And can I use that? And maybe, no, it's here. No, you can't do. It's a bit hard, so we typically don't do that, but rather splice it off or partition it off so that each node has its own range of IDs where it can assign IDs to. Thankfully, thanks to Christoph, we already have that, so that is not a problem. With the problem that it's only 16-bit, so when you splice this up, you end up with actually a very low number on either thing. So either you allow for more connections and then drive down the number of nodes, or you end up with having more nodes, but then drive down the number of connections per node. So, yeah, all a bit bad, and everyone is complaining about this, but that's the way it is currently. So we are still trying to figure out a way how we can overcome that, but in the meantime, well, it's there, so right, okay. So just I split it in half, make it 8 bits for the nodes and 8 bits for the connection. It's still 255 nodes in the cluster, which is about fine, because that means I just can use a class C network and, okay, good. So, and there are some other things which are there, like port IDs, which is one of these annoying things, a really annoying thing, and the ANA group ID, which technically also needs to be unique per subsystem, but we decided to keep it globally unique, so suddenly I have a globally unique value which I need to care about. Okay. And all of this needs to be synchronized across all nodes in the cluster. But then we have etcd, which, remind me again, was a distributed database, so we can store data in it. So we can use that to synchronize all these values. And the really neat thing is that we can actually flatten out the config.fs hierarchy to become a key value store and just push all values from config.fs up into etcd, such that etcd has a direct copy of the contents of config.fs. And yeah, and of course, insert some magic here to ensure that all the partition values are correct, of course, as you do. And then these values are in sync. So now we have a cluster with an etcd one and an NVMe target on top, which also talks to etcd, which actually the etcd is the same one, but I just put it like this to have a nicer picture. Otherwise, the errors would be going all over the place, and right. That looks nicer, even though it's not correct. Right. Now we have a distributed cluster. Isn't that cool? Yes, that is totally cool. But we might want to configure that thing. Yeah, for that, we do have config.fs, which allows you to configure a node, not the cluster. So, okay, right, but we just pushed the config.fs structure into etcd, which means etcd now contains a global view of the cluster. So we can reverse that operation and basically unflatten the values which are in etcd. And then we have, well, something which looks like a file system structure. So we can make it a file system structure, you write a fuse frontend on top, and then mount that fuse frontend on top of the original point of that config.fs. Putting things on top of other things, right? There we go. Which actually works quite nice, because now we can use NVMe CLI to configure the entire thing, which is just awesome. And you can just put it on any node in the cluster, wherever you want, just load the fuse file system, configure that thing, unload again, there you go. So, and I thought, hey, that is cool. But again, then I did that and said, oh yeah, it's great, but no, not so great. Because it is a distributed cluster. And which means you actually have to have the nodes, meaning the machines for that cluster. And if you want to, say, scale out, it means that you actually have the number of machines you need for doing that cluster thing. While you could, of course, do it via VMs, then I said, oh, come on, where's the fun in that? Because, well, you know, it's etcd and everything. We could just see to push things into a container, and then we could run everything in a container. Wouldn't that be awesome? Yes, it would, but then turns out that config.fs is not namespace aware. So any configuration you put in via config.fs is actually global for the system. So when putting in the container, everyone will see the same configuration, which is kind of defeating the purpose of a distributed cluster. So I actually started writing on making config as namespace aware, which it's nearly done now. So then we have a config space, namespace aware config.fs, and we can just mount config.fs in all container instances and have a per container view on that config.fs. So we can do it like that. So that was actually quite a neat idea. And yeah, so patches are in progress. And then you can have the whole thing in containers on your local machine without having it to bog down via tons and tons of VMs. That is cool. And there's the other thing which I presented in Zagreb. I think, yeah, I did. So we can now simulate log pages, because the thing is, NVMe needs to detect the nodes, or needs to detect the topology. That's done via something called discovery log pages. So essentially, you just connect to the device, get the log page, and the log pages tell you where the other nodes are, which is fine. But in our case, these log pages are actually generated in the kernel. And the kernel obviously only knows about the local configuration, not so much about the global configuration, because that configuration we just abstracted out into etcd. So the kernel has no idea what we're doing there. Which means it doesn't really work. We have a nice cluster, but we wouldn't know what the cluster looks like. So what I did is I implemented an eBPF hook for in the kernel for the target site to inject arbitrary log pages. So you can just put in log page via eBPF, and then that would be used instead of the in-kernel generated one. And with that, we can easily generate a discovery log page containing all information in the cluster, push it in, and everyone would think, hey, it's a real cluster, which is cool. So what that means, hey, we now have a cluster thing, and that actually was it, that one. I do have, maybe, if that works, if I get the mouse, there's the mouse. Need to get up. Okay. Can do just, let's see if I can do something here. So So there is now a VM with these. Right, okay, so VM thing. What do I present this one here? Oh, yeah, come on. It's. Yeah. Was that correct? No, you can do this. No, I can't. Yeah. Is it? I heard that. Right. Okay. So, and that is now the setup running in containers. So here we have here the etcd cluster running. That one there's the etcd cluster running, and these are the Sheepdog nodes on top of the etcd cluster. And I expose the ports of the Sheepdog, so I can now use the local command to look at the cluster, and ta-da! And there you see, there's the cluster. It looks just like a normal cluster, and I can then look. So, yeah, it is a bit. You have to work on the display here. This is a monitor would be nice that we know what's happening, and that is then the the VDI in that cluster. So, right, and I can. So, and this is the VM which has the, as you can see, the patches for the distributed for the namespace where config.fs. So we are here in the on the root file system, we're in the root namespace, and there you see a subsystem there. Then we can split things off. So move into another namespace. And then we mount the namespace, config.fs namespace for us, and can create our own subsystems. And there you see, we have our namespace, our own subsystem, and it's completely insulated from us. And then we can and in fact just visible to us or to that namespace. And then we can just say, all right, now I'm going, then remove it again. Unmount the thing, and then we can and then you see, and here we're back to the other one. So, and that's the presentation, basically. Any questions? Oh, silence in the room, that's good.
So you distribute the storage using the NVMe characteristics, or how does it? Is it just one? Like, is the storage actually distributed, or you just access one?
No, that's actually distributed.
Yeah. So but it's on the NVMe level then.
Yes.
Yeah.
Yes.
Okay. Cool.
It's the NVMe
because
level.
I was just going like, what the hell?
So no, it's actually on the NVMe level. So that thing will then appear as basically a multipath system, and you can just as the VDIs are accessible from each node, so you can just make connections to each node, and then you can access multipath-wise to each node. And you can even be a bit more clever to try to do I/O steering, because then you can try to figure out right on which on the nodes this particular slice is present. So you can then, that's one of the things which I want to explore. Then we can see if we can't redirect I/O to that nodes which actually hold the slice.
Cool.
Did you do some benchmarking? Sorry.
I'm happy enough that it works, and that MKFS, that I can create an XFS file system. So that I'm quite happy with.
I mean, that's cool.
Come on.
Yeah.
No, I didn't.
Okay.
But yeah, that will be one of the next things. Yes.
Since you're creating a lot of NVMe's, will it work with making array collections? You get an array of NVMe drives that is distributed over a site?
That is actually done on the Sheepdog level, because Sheepdog actually has erasure coding on the slices. So you can configure that Sheepdog internal does erasure coding on the slices. So, and that should be giving us enough of data integrity checking that we wouldn't need RAID on top. That's the hope, at least. Because alternatively, there's only, RAID would only be required if you somehow think there might be I/O errors or some errors during.
The idea is that you can make a array that is distributed over many locations.
Yeah, but that's basically what erasure coding would do the same thing.
Exactly. Yeah, that's erasure coding. That's why we do erasure coding on the Sheepdog level. So, and so it already does internal RAID to all intents and purposes. Okay, then thank you very much.
Thanks again.
Was there another one?
There's one more.
Yeah. Sorry.
One final.
So maybe this is a stupid question, but the whole point of this is just to test the NVMe code. Or do you actually want to use this setup for anything practical?
I surely will want to use the setup, and surely for something. Yes. So the answer is definitely yes. No, at this time it's just a test bed really to see if can we do or can I do a distributed cluster, and does it actually work, that whole thing with all the various component integrated blah 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 whatnot, and then also to see right, okay, what can we do with it. And so prime target here really is to as a development thing that one can test out new features, new things, just see how it behaves then. And once I get around to actually do some real measurement, then I'll see how good it actually is, how performant the whole thing actually is. Currently, I have no idea. Could be anything.
All right. Okay.
Okay.
Thanks.
Thank you.